Hi, and thank you for joining. Let's continue with example number 5. We are practicing how to use a second derivative to determine the concavity of a function. So far, we've looked at several polynomial functions, and this is an example of a rational function. So to determine the concavity, we need to study the sign of the second derivative. So to find the second derivative, we need to first find the first derivative. So dy dx equals, so we are using the quotient rule in here because this is a rational function, and remember that quotient rule states that if the function is in the form y equals f over g, then the derivative of a dy dx would be f prime g minus g prime f divided by g squared. So let's do this. Derivative of 6 is 0, multiplied by the denominator x squared plus 3. Then minus derivative of x squared plus 3 is 2x. Multiply this by 6. Divided by x squared plus 3 to the power of 2. Let's simplify. So 0 times anything will be 0. So the numerator will host only one term. So negative 2x times 6, negative 12x. And the denominator has x squared plus 3 squared. dy dx, everyone. So here we go. We're going to find the second derivative based on the first. So d squared y dx squared equals derivative of negative 12x is negative 12. Multiply this by x squared plus 3 power 2. And then minus. So we are differentiating the denominator now. Remember that there is a small little chain here again. So we'll differentiate the outside function, so the power of 2, and then the inside of it. So the outside derivative will be 2x squared plus 3. So the expression inside brackets won't change, but the power of 2 will reduce by 1. So 2 minus 1 is 1. Multiply by the derivative of the inside, which is the derivative of x squared plus 3, which is 2x. Remember, derivative of 3 is 0. Now, this is simply the derivative of the denominator right here. We have to still multiply it by the numerator, so according to the formula. So the derivative of denominator times the numerator means that we're multiplying by negative 12x here. And this entire thing will be over x squared plus 3 squared brought to the power of 2. Let's simplify it. So we have negative 12 x squared plus 3 to the power of 2. Remember, we have two groups of terms in here. They're separated from each other by this minus sign here. So we do not want to expand here right away. It's going to be a lot of work. And the number one reason is actually the fact that we are going to look for common factors. So what we do is we try to simplify as much as we can in each group of terms. So the first one, there is nothing we can simplify. You just leave it in factor form as is. In the second group of terms, you can combine the monomials. We can always combine monomials, and we should combine monomials at any time. So negative 2 times 2x, negative 4x, times negative 12x will give positive 48x to the power of 2. And then we have x squared plus 3 to the power of 1. We don't need to write that power. And this will be divided by x squared plus 3 to the power of 2 squared will be a power of 4. So we're going to take out the greatest common factor. And for this, again, remember, keep an eye on the fact that we have two big groups of terms. So this one and this one, separated by a plus. So we will have to find the common factor from each monomial first. Negative 12 and 48x squared have a 12th in common. I will take the negative one out as well. So we have negative 12. Actually, we can keep the 12th in here, just the 12th. And inside the brackets, we have x squared plus 3. That is to the power of 2. And then we have x squared plus 3 brackets again, but to the power of 1. So it seems that x squared plus 3 is a common binomial. So we take the lowest power out. And now let's check and see what we are left with. So from the first group of terms, we have taken out 12, so we have the -1 inside. And then we have x squared plus 3 power 2, so 1 power is out, so 1 power must be in, so x squared plus 3. From the second group of terms, we had a 48 with 12 out. The 48 will become a 4. X squared is all in, and x squared plus 3 is all factored out, so close the brackets. And all this will be divided by x squared plus 3 to the power of 4. So a couple of things that we need to take care of here. You see that x squared plus 3 is a factor in both numerator and denominator, which means that they can reduce. So this is a power of 1. Down we have a power of 4, which means that the denominator would be to the power of 3. So 4 minus that 1 power here. Number 12 is where it was before. We'll simplify inside the brackets. So as you can see, inside the brackets, we have this wonderful expression. So negative x squared minus 3 and then plus 4x squared. It seems that there is more simplifying we can do here. So what I'm going to do actually is make this a tiny little bit smaller so we can organize our solution here. Or else I'm going to zoom in so we can see it. All right, so we're still doing the second derivative. We're not done yet. And what we see is a 12. 4x squared and minus x squared will give 3x squared. And then minus 3. All this over x squared plus 3 to the power of 3. So we're almost there actually, and we can use the equation of the derivative, second derivative as is, or we can factor it some more to prepare it in order to find the zeros. So in this case, what we have is also 12. We can take 3 out, and then we have x squared minus 1. Denominator x squared plus 3 power 3 still. And here we go again, one more step. We'll combine the 12 and the 3. So we'll have 36 x plus 1x minus 1 over x squared plus 3 to the power of 3 equals the second derivative of this function. So I will box this up because we're going to work with it a little bit. So we are now studying or ready to study the sign of the derivative, and because the derivative is in rational form, to study the sign of it, we need to consider the signs of both numerator and denominator. So we're going to grab this one here. Let me just bring it up. Just organizing the solution. There is no significant step here. So we're looking at the numerator. Remember that the sign of a rational expression is dependent on the signs of both numerator and denominator. So we'll say that for the numerator, we have the zeros at wherever 36 x plus 1, x minus 1 becomes 0. So which happens at x equals -1 and x equals +1. In the denominator, which I can see if there are zeros in there, so x squared plus 3 to the power of 3 will be equal to 0 if x squared plus 3 is 0. Or we're going to say if x squared equals -3, which makes x equal to plus or minus the square root of -3. Since the square root of -3 doesn't exist in the set of real numbers, then we're going to say that there are no possible real values that can make this expression equal to 0. So the fact that this expression is never 0 means that this expression will either stay always positive or always negative. Now, as you can see, this is a quadratic expression. And when you look at a quadratic expression from the graphical point of view, in this case, it's very easy to draw the graph of it because it's a parabola, basic parabola that is opening up, vertex right here at y equals 3. You can tell that the parabola will never meet the x-axis. It's opening up and it's never down, further down enough so that it intersects the x-axis. And that makes the parabola have, or the y values of the parabola or the y values of the function always be positive. So what that tells us is that the denominator will never equal 0, so there are no restrictions, and the denominator will never be negative, it will always be positive, which means that the sign of the second derivative will be dependent only on the sign of its numerator. So when we study the derivative, we draw the number line, and the only numbers we need to plot in there are the values of the zeros of the numerator. So from negative to positive infinity, we had the key values at -1 and +1. The sign of the derivative will depend solely on the sign of the numerator. I will write the derivative, the entire thing here. And then x squared plus 3 power of 3. And down here, we'll write the nature of the graph of the function. Nature of y. So derivative will have zeros at 1 and -1. And let's take a look at the sign of it. So we can actually discuss the sign by simply drawing the graph of x squared minus 1. This would be a parabola that opens up. 36 is a positive coefficient, so it doesn't play a role in changing the sign of the derivative. So that means that the derivative will have negative values between its zeros and positive values outside it. This will make the graph of this function appear to be concave up, concave down, and concave up again. Now, at x equals -1 and +1, as you can see, the concavity has changed, which marks these 2 points as points of inflection. All right, so there will be a point of inflection at -1 and a point of inflection at +1. So if you want to find the y value at each point, then we simply have to substitute the value of x into the equation of the function. So we have 6/4 or 3/2 here, and y equals 6/1 squared plus 3. Again, it's going to be 6/4 or 3/2. So the point of inflections will be at points of inflection will be at x equals -1 and y equals 3/2, and x equals +1, y equals 3/2. And what this tells us in the meantime is that at two opposite x values, we found same y values, so there is a high chance that this function will have even symmetry. Let's take a look at its graph. So at this point in time in this lesson, we haven't learned how to graph or analyze or complete a full sketch analysis of a curve. So y equals 6 divided by x squared plus 3, we said. And as you can see here, this would be the graph of the function. We have seen these functions before. These are the functions with no vertical asymptotes. We have analyzed them in details in advanced functions course as well. Let's see. And let me just place the graph somewhere in here. If you would like to actually check your answers at home, these are hyperlinks of the exact same graph in here, but I cannot access them from GoodNotes because GoodNotes will change or turn everything into a picture. So at x equals -1, we said, and +1, we'll see points of inflection. We see the graph of the function is concave down here, and it's concave up on the sides. All right, and voila, there you go. This is how we use the second derivative to discuss or to analyze the concavity on the graph of a function, of a rational function to be more precise. So in the next example, we have example number 6. We have something slightly different, so we'll talk about it in the next recording. Thank you for learning with me, and you have a wonderful day. Bye for now.